Welcome back to Robot Cantina. Today we have a cool fuel economy experiment to show you. So in this episode, we're going to install a robotic throttle on our project car, and through the magic of electronics and software, we're going to make the car get better fuel economy no matter who drives it. This one's really off the hook, but it works. Come on and check it out. Now, way back in the day when these Detroit dinosaurs roamed the streets, a common way to improve fuel economy was to get yourself a vacuum gauge from J.C. Whitney and connect it to the intake manifold on the engine. Well, the gauge itself really didn't do much, but if you closely monitored the gauge and manipulated the throttle so the car went down the road with the gauge reading the highest vacuum possible, well, you'd get a lot better gas mileage. Now, a lot of folks equate this method of driving by placing an egg between your foot and the accelerator pedal. And obviously that means in order not to break the egg, you depress the accelerator very gently. Well, this trick helped a lot of folks save a buck or two. Now let's fast forward a little bit and start throwing some technology at this jalopy. Well, the first thing we can do is replace the vacuum gauge with a map sensor. In its simplest terms, a map sensor is basically an electronic vacuum gauge. Most of the older fuel-injected and some carbureted cars built here in the States have these sensors. Anyway, the map sensor will give us a way to measure the vacuum electronically. So let's add another part to our cartoon, and that is the drive-by-wire throttle body. Now, this gizmo is just an electronic version of a standard cable-controlled throttle body. This throttle body needs electrical signals in order to open and close the throttle, and that'll come in handy for this experiment. Of course, now we need a computer, and for that we'll use a $23 Arduino Uno. Uno means one in Italian, but that's not relevant to our story. Anyway, now we can connect the map sensor and the accelerator to the computer, and the computer will generate signals to open and close the throttle body. Of course, we'll need to write some clever code to make all this work. So the code will act like an egg between the driver's foot and the accelerator pedal. And bloop! Now we basically have an Arduino between the driver's foot and the accelerator. Alright, well let's clear the slate and get into a little bit more detail. That's better. So let me take a minute and remind you folks that fooling around with drive-by throttle bodies is extremely dangerous. Now, there's been many cases of unintended acceleration that have ended with tragic results. Pretty much all modern cars with drive-by-wire have redundant safety features that will disable the throttle if a fault is detected. It's annoying, but it's a necessary evil. Now, I have 25 years experience in automotive electronic engine controls and automation. I write code in several different languages. And with that said, even I'm uncomfortable with certain aspects of this experiment. Alright, well let's continue with some more details. So let's start with what we already know. The first thing is the Arduino. We'll connect the map sensor to one of the analog channels so we can read the vacuum the engine develops. Next, we need a way to measure how much the driver presses down on the accelerator. Now, this is actually really hard to do, but we're going with an ultra simple solution, and that is to use the throttle position sensor on the throttle body already mounted to the Saturn's engine. Yeah, that's right, we're going to leave the original throttle body exactly where we found it. You see, this throttle body is already connected to the accelerator pedal, and there's a cable that connects the pedal to the throttle body. And of course, pressing down on the pedal will ultimately change the throttle position, and we can send that signal directly to the Arduino. It'll make more sense in a moment. Now pay attention, what we do now is very unconventional. So the drive-by-wire throttle body gets mounted directly in front of the throttle body already on the engine. So basically we have two throttle bodies in line. Now let's go back one step. Alright, so now we're looking at the stock mechanical throttle body that's already on the Saturn's engine. Try not to overthink this and just follow my lead. We'll be using this throttle position sensor to feed the Arduino, and we'll be using the throat of this throttle body to mount the drive-by-wire throttle body. Now this might be tough, but pay no attention to this throttle butterfly. It really won't affect our experiment, and I'll show you folks how it all works on the bench in a minute or so. So with the stacked throttle bodies, we simplify all sorts of complex stuff, and as a bonus, if the drive-by-wire throttle body or the Arduino goes bonkers and we get a runaway throttle, well, just letting off on the accelerator will quickly resolve the situation. The system is really simple, and I just got word from future Jimbo that it works just fine. Yeah, buddy, it works fine, no worries. Thanks, Jimbo. Anyway, back to the story. This drive-by-wire throttle body has two completely independent throttle position sensors. We'll need to send one of the throttle position sensors to the Arduino, and then we'll send the other throttle position sensor to the PCM that controls the Saturn's engine. So now the Saturn's PCM will be happy, and it'll have no idea we're doing shenanigans with the throttle. Now unfortunately, the Arduino doesn't have enough power to directly drive the electric motor that opens and closes the throttle in our drive-by-wire throttle body. So we need to add something to amplify the signal, and that's going to be this full H-bridge thingy. Now this guy is rated for something like 30 amps, and our throttle body only consumes about 1 amp. So this H-bridge is way overkill, but it's cheap and only costs between $6 and $8. Anyway, it interfaces between the Arduino's digital ports and the throttle body's electric motor. Now the software that makes all this work is a basic servo feedback loop, with enhancements of course. So the Arduino and the H-bridge are packed inside this project enclosure to keep everything neat and in order. And now you can see we have more stuff on the outside of the box. Well, the software pretty much does everything, but there are some unknowns. So we had to add 2 fine-tuning knobs and a switch to disable the enhanced features and allow the throttle body to still work. So this knob sets when the system should engage. You see, turning this knob counterclockwise tells the system to modulate the throttle for higher vacuum, thus higher fuel economy. And turning the knob clockwise tells the system to modulate the throttle for lower vacuum and less fuel economy. There's a trade-off. Higher vacuum equates to higher fuel economy, but you also lose the ability to generate any horsepower, and the car will be dangerously slow. So ultimately, we need to find a balance between fuel economy and power. So that's why we made this adjustable. Now the bottom knob will adjust how fast the system will react. Now if it's too fast, the engine will start to surge, so slower is better. But if it's too slow, we'll lose some fuel efficiency. So we made this one adjustable, and it's something we'll have to adjust once we take the car on the road. And this switch here, well, it tells the software what mode to be in. When the switch is on, the computer will optimize the throttle position at all times, and that can be annoying. Now, turning the switch off, that turns off the fuel-saving features and allows the drive-by-wire throttle body to function like a normal throttle. Let's take a better look at this stuff on the bench. Alright, cool, now we're making some progress. I'm sure a lot of you folks want to see this gizmo work. But first I need to give a shout out to House Cleanup 818 out in Granada Hills, California. They sent some really cool Ferrari decals to our P.O. box. Now if you squint a little bit and take a look at our Saturn coupe, why sure, it really does look like a Ferrari. A Testarossa as a matter of fact. You know, Testarossa means redhead in Italian. Yeah, the things you learn on this channel. Anyway, we'll be putting these decals on our Saturn Testarossa, and hopefully that'll impress the chicks. Hey, and thanks again House Cleanup 818. Alright, now let's get back to the video. So this is the throttle body that will mount directly to the engine on the Saturn. Like I mentioned earlier, this is just a normal cable-controlled throttle body. It's also a convenient mounting base for the throttle position sensor that we'll be monitoring with the Arduino in this box. So moving this throttle sends a signal to the Arduino, and through the magic of software, that signal is transferred to the other throttle body. Here, check it out. Pretty cool, huh? Now the drive-by-wire throttle body has a custom 3D printed flange that slides right over the throat of the other throttle body. Yeah, I know, this is definitely weird. So now you can get a better look at the 2 throttle bodies in action. And the best part is, if we have a malfunction and the drive-by-wire throttle body goes wide open, I just take my foot off the accelerator and problem solved. I really like that feature, and I reckon the double throttle bodies can hurt performance at wide open throttle, but in today's experiment, we're not going for the land speed record. So it'll be fine. Unfortunately, I can't demonstrate the fuel saving feature on the bench. For that, we'll need to mount this in the car. Alright, so we have the Robo-throttle mounted up to the Saturn engine. We had to spend a little bit of time adjusting one of the variables in the software to correct an idle issue, but that was no big deal. We did find out that there's absolutely no room left to install the air filter system, so we ain't gonna run an air filter. I mean, this car is 25 years old and its days are numbered, so I'm not too concerned. I guess I should mention, this car is also set up for the lean burn experiment, but today we're not doing any of the lean burn stuff. So let me give you a quick overview on the lean burn. The engine's equipped with a factory narrowband oxygen sensor, and it also has an innovative motorsports wideband sensor. Now we use a small signal relay to switch between the sensors, and today we'll be using the factory narrowband sensor. So in other words, the lean burn stuff is completely disabled via a switch, and it'll stay disabled throughout today's test. Inside the car we have the Robo-throttle control box sort of taking up precious space on the passenger seat, and it's within arm's reach, so I can make adjustments to the system once we're underway. I say it's time to take this science experiment on the road. Okay, so the engine starts, that's a good sign. We have throttle authority, so things are looking really good. A quick check and yep, the system's fully engaged. Now we're going to start this adventure with the Robo-throttle fully active, and that's just for fun. Right away I can detect the throttle is working to some degree, but I'll have to dial it in while we drive. So off camera with my right hand, I'm adjusting the automatic throttle engagement point, and I'm also adjusting how fast the system will correct the throttle position. If it's too fast, the engine will start to surge, and if it's too slow, well, we'll lose some fuel efficiency. It's a delicate balance. Now I'm also watching the scan gauge for instantaneous miles per gallon, throttle position, and map pressure. This scan gauge can show up to 4 readings at the same time. Here on the straightaway, I'm trying to get the car to go as fast as possible. Now the Robo-throttle doesn't limit the vehicle speed, it only limits the throttle angle, and the vehicle speed will creep up to around 65 miles per hour. The goal is to adjust the system so the car goes at least 60 plus miles per hour and returns the best fuel economy possible as displayed on the scan gauge. Now this is a simple system and the computer only monitors the map sensor on the engine, and then the computer will modify the throttle angle and try to hold the throttle in a position where the map sensor is indicating the best fuel efficiency. We could certainly add more stuff to monitor, but for proof of concept the map sensor is all we really need right now. No sense in building something incredibly complicated, then having to spend days troubleshooting and tuning the system. What we have today is pretty much all we need for our test. As you can see, the speed is creeping up as I fine-tune the control box. Now at this point it's clear the system works exactly as designed, and I'm really stoked that all the software is behaving. Keep in mind this system was bench-tuned in the workshop, and this is the first time it's being road tested. So we do all our testing out in the middle of nowhere, and for the most part, we're the only ones on the road. Occasionally we do encounter traffic, but it's not what I'm used to when I grew up in New York. I reckon that guy was on his way to the airport or something. Such a big car. So let's take a look at the scan gauge, but first let me explain a few things. This scan gauge is basically the only feedback that we're using to tune the system. The gauge is connected to the car's OBD2 port and is in no way connected to the Robo-throttle. So here's the average miles per gallon. Don't pay attention to that right now, but I have found this to be very accurate. This is our instantaneous miles per gallon, and this is the number we obviously want to go as high as possible. Over here is the map sensor. This signal is also being fed to our microcomputer, and today we want to keep this number between 7.5 and 8.5. I'm not sure what units the scan gauge is reading, but with this setup, a lower number equates to better fuel economy. It's kind of backwards from a vacuum gauge that reads in inches of mercury. Now here's the throttle position. The throttle position on this gauge is reading the position of the throttle in the drive-by-wire throttle body, or the Robo-throttle. Now our system reads the map sensor and will actively adjust the throttle position in order to keep the map sensor reading between 7.5 and 8.5. As I mentioned at the beginning of the video, the throttle position directly affects the map sensor readings, and the map sensor data is a good indicator of fuel economy. Okay, so now we're going to roll the video. Watch this, and this. Also keep in mind that I have the accelerator pressed down quite a bit, but that doesn't matter, because no matter how hard you press on the accelerator, the computer will automatically compensate and adjust the throttle for maximum fuel efficiency. It's pretty cool how the Robo-throttle is able to force the engine into maintaining decent fuel economy. I do think we can tighten this up a bit for more stability, but after all, this is the first outing. Now we'll show you a typical acceleration run with the Robo-throttle engaged. Theoretically, the Robo-throttle should not be engaged while accelerating, because this affects performance way too much. We have a few modifications to the code in mind to help with acceleration, but that's for another day. Anyway, it looks like the Robo-throttle is working pretty good. Let's top off the fuel tank and do a fuel economy test. So today's test will be at the bigger hillbilly proving grounds in rural Kansas. This is a 33-mile loop out in the middle of nowhere, and we'll try to get in about 200 miles. Now I should mention this road here can be busy at times, so when we accelerate up to speed on this stretch, we'll momentarily deactivate the Robo-throttle so we can get the car to accelerate without causing a traffic jam. Alright, let's do this. Alright, well, we have some data to look at. Let's see if the robot can manage the throttle for better fuel efficiency. So after the system was dialed in for best performance and maximum fuel economy, we put down 204 miles and consumed a total of 4.3 gallons of gasoline. Now that calculates to a solid 47 miles to the gallon, and that's pretty impressive. Keep in mind, it didn't matter how much I mashed down on the accelerator, the actual throttle was being actively managed by a computer, and the computer optimized the throttle position within the limits that were set. So, basically anybody that sits in the driver's seat will effectively get the same fuel economy. Now, how much better is the robot throttle than a human? Well, that's a good question. Previously I managed to get 42, and we even got 47 miles per gallon for our baseline data on the lean burn experiment. But on both occasions, I was very mindful of my driving habits, and both trips required extreme concentration while driving. I reckon I really don't know how well this car would do if it were driven with no concerns to fuel economy. Perhaps we need to know that before we can continue. I'll be right back. Now for this test, what we did was we turned off the throttle management feature, and without this feature the throttle input matches the throttle output, or in other words, the system just mimics the exact inputs from the driver and does nothing to optimize the throttle position. Well, we got some more data. So we put down 137 miles and consumed 3.5 gallons of gasoline, and that gives us the answer we were looking for, and that's 39.69 miles to the gallon, which ain't too shabby, especially since zero effort was made to economize. So the Robo-throttle does help, but it can't pull a rabbit out of a hat, and what I mean by that is, the robot throttle doesn't do anything except manage the throttle, and that's something a semi-skilled driver can do. So basically the robot throttle takes the human error out of the equation. Now keep in mind, this was the very first test of the system, and well, there's certainly room for improvement without affecting performance. And although this is only speculation, I feel I can squeeze a little bit more out of this system. I think some of you folks would agree this is a pretty cool gizmo, but I'm not sure this is something that could be tolerated on a daily basis. After all, it's very Orwellian, sort of like having Big Brother forcing you to behave a certain way. On the other hand, I can see this gizmo as a tool, and what I mean by that is, with a little bit more refinement, it can be incorporated into one of our project cars to factor out the human element for our various tests. Yeah, so that way, any changes we make to the car, well, the results would be based on the exact same driving habits, if that makes any sense. So some of you folks may be saying, Jimbo, this is definitely a cool system and has mainstream applications. Well, perhaps. Let's see how well the car performs in the 0 to 60 acceleration run while the throttle is being fully optimized. So, the way the throttle is programmed, you don't get a lot to work with, as you can see. The best way to get the car up to speed is to hold it in each gear until the engine falls flat on its face. Of course, all this can be fixed with a few lines of code. Yeah, everything was going great until this tough guy shows up. So I lived in rural Michigan for a number of years, and I know what these things are. I'm not a total idiot.
Dumbass.
But keep in mind, I grew up in New York. I guess that shows. Now, I don't hunt, but if I did, it would be with a bazooka or possibly a self-propelled howitzer if I could get my hands on one. Ah, there's this dumbass again. I say we head back to the shop and look at the data. Back in episode 15, we recorded a 0 to 60 time of 13.96 seconds. And well, that ain't so good. But after all, we're testing a crappy 25-year-old Saturn with a pathetic base engine. Now, with the fully optimized Robo-throttle, we got the 60 miles per hour in, well, you can read. Yeah, that's not really good, but a minor change to the code would absolutely fix that, and the performance would likely be fully restored under hard acceleration. But the fuel economy would also suffer. Anyway, for safety reasons, we really should modify the code to allow full power while in economy mode. But today, we'll show you all the drawbacks. So we have one more test we need to finish on the Saturn before we do the diesel swap. And that's the conclusion to the lean burn experiments. Hopefully by the next episode, we'll wrap it all up. But this ain't the end of the Saturn experiments. As some of you may recall, we picked up another project vehicle so we can continue with random experiments. Now this car has some problems for sure, but we sourced all the parts necessary to repair it and put it back on the road. So you can definitely look forward to more crazy stuff, and we can also start with the epic diesel swap on the coupe. Well, unfortunately that's all the time we have today, and I hope most of you folks come on back. If you want to stay informed, please consider subscribing. That really helps us out more than you can imagine. And if you enjoyed this video, click on the like button. That helps us know we're producing the content the viewers want to see. Well, until next time.